Okay, so we're going to talk about redox coenzymes. So this is what happens when we do redox reactions in biological systems. So this is what our body does. So remember I talked about earlier, we don't just run a combustion reaction. We break it down into pieces. And so combustion is like a 100% complete oxidation of an organic compound. You can't fit any more carbon-oxygen bonds on there than if everything's CO2. And so that's where you end up. So in our bodies, what we're doing is we're performing a combustion reaction, but we're breaking it into a series of smaller redox reactions, smaller oxidation reactions. And we have to have something that soaks up those hydrogens out of those reactions and is essentially used to take little pieces of the energy away. That's what these do. And we'll talk about the role they have in that in the next video. So what they're really doing is they're carrying electrons, but for now, just realize they're soaking up hydrogens. Those hydrogens have electrons though. They're not H pluses. They are hydrogens with an electron on them, and those electrons are going to be used to do work and generate a whole bunch of ATP in respiration. So that's kind of a preview of where we're going. All right, so these redox coenzymes, there's two of them. There's NAD and FAD. All right. So NAD plus is, so these are both hydrogen acceptors. And so for NAD plus, now it's not a coincidence, by the way, before I write what it's a hydrogen acceptor for, that we have, remember we have two types of redox reactions, and we have two coenzymes here. So guess what? One of these coenzymes is going to pair with one type of redox, and the other one is going to pair with the other type. Okay, so NAD plus is going to be used to accept hydrogens when you are dealing with changing the number of CO bonds. All right. So if you're changing the number of CO bonds, NAD plus is involved in there somewhere. We're going to show the chemical equations, and we're going to have the full balanced redox reactions now when we're done here. So if this is handling the number of CO bonds, well, guess what this is going to accept hydrogens for? What's our other type of redox reaction or oxidation reaction? So, you know, if changing number of CO bonds is already off the table, what does that leave? Well, dehydrogenation. Now, the one thing I'm going to say is I'm being very exact with the language here, or I'm using exact language. Like this is, if you see dehydrogenation reaction, this is the coenzyme. Nature is a little finicky. It's not 100% true. More often than not, FAD is going to pair with this type of reaction. NAD plus is going to pair with this type of reaction. But they're not. It's not 100% of the time here and here. It's a little fuzzy. So biological systems get a little bit messy. Not just when you're dissecting them either, but when you're studying them. And so, you know, be aware that this isn't a set in concrete. This is not carved in stone. This is a general trend that I'm just making more than a trend for this class. So, what do these reactions look like? Well, when they absorb, so first let's talk about what happens when they absorb hydrogens. What do they do? Well, if you're talking about NAD+, it's going to accept two hydrogens, and these are going to be from some organic molecule. And it's going to become NADH, and then you're going to get an H plus out of it as well. Whereas with FAD, it's still going to absorb two hydrogens, but it's just going to become FADH2. And so when these come from an organic molecule, well, this one would be from an organic molecule that is gaining carbon-oxygen bonds, whereas this one would be from a organic molecule that is gaining double bonds between carbons. And so let's put the whole thing together now. Let's bring in, the stuff we had before with these new ideas. And so this will give us a fully balanced chemical equation. If I can get this piece of paper out of the way, there we go. Launched it across the house. My house isn't that big, so it doesn't say a lot that I did that. That said, I'm sure I'll win the Olympic gold medal for launching paper. Alright, so what am I saying here? Well, biological systems are a little messy. So let's give an example that's a little bit busy. Spider just tried to run up on my screen. It's coming right through here. I saved you all from a terrifying little spider. Alright, where was I in drawing? It distracted me. It's already one. Alright, we have an OH there, double bond O, double bond O. This is known as succinic acid. Now I'm jumpy every time I see anything. Alright, so what we're going to do, I'm going to hold off here. There's going to be space for something else here. But here's what we get. Here's what our molecule is doing. Here's what's happening with our organic compound. Plus something else here. Okay, so we get, this is called fumaric acid. You don't have to know these names, I just like to throw them out there. These are both molecules that are part of biological systems. So I didn't just make them up to be cruel, like this is the type of thing you're dealing with. So I was trying to train you earlier to look a little bit past functional groups. If they show up on the left and the right, they're not part of the reaction, they're not changing. They're just part of the molecule. So what did change? Well, I went from a single bond to a double bond. Well, that means I'm missing two hydrogens. This was a CH2, this was a CH2, now it's a CH and a CH. So there were, just to write it out, there were two hydrogens here. Now there's just one. Where did the other two go? Well, they went onto our hydrogen acceptor. So the molecule has two less hydrogens. And we're changing the number of carbon-carbon double bonds. So that means that FAD is going to be involved. And so we're going to get FADH2. It's as easy as that. So this is a fully balanced chemical equation. Why don't we look at, a reaction here with our good old friend ethanol. Alright. So, this was an oxidation, by the way, right? This was a dehydrogenation reaction. So let's do one more oxidation here. And we're going to go plus something gives me the following and something. Well, this is an oxidation, so I am going to lose two hydrogens off this molecule. Because, again, I'm going to sketch them on here for illustrative purposes. This carbon is making 1, 2, 3, 4 bonds. There's no hydrogen here, so I went from having 3 hydrogens in this area to 1. So there's 2 missing. Where did they go? Well, they went to their hydrogen acceptor. Now which one do I use here? Do I use NAD plus or FAD? Well, as you see above, FAD would be for when I'm adding double bonds. So it must be NAD plus because I'm changing the number of carbon-oxygen bonds. And so that means I'm going to get, NAD H, and I'm going to get an H plus. So I actually get 2 more things over here. Those are separate. Alright, but what if we're doing a reduction? What do we do there? We'll just flip these guys. That's all we do. So let's say we have something like this, plus whatever, gives me an alcohol and something. What do we do? Well, I'm changing the number of carbon-oxygen bonds, so NAD plus is going to show up somewhere, but I'm doing a reduction, so I'm doing the opposite. So that means that NAD plus is going to be over here. And so this is where I have my NADH and H plus. So they can be hydrogen donors as well. So they're acceptors in oxidation reactions, and they're donors in reduction reactions. So really what these are think of them as like hydrogen transports. Like you never just load a truck and then leave it forever. I mean, well, okay, so the Soviet Union was kind of known for that. Like they would literally just ship trains full of food places, and they would just go there and rot because, like, I don't know, paper said send it that way, so they just send it that way. And then no one ever got a paper that said unload that train that just showed up. So they literally just have like food rot in train stations. But outside of that example, you don't tend to just put stuff on a train and then, oh, the spider's back. Whoa, there it comes. It's on camera now. All right. I wasn't making it up. There really was a little spider in here. I don't usually, I'll be honest, I'm not a spider killer. I just take them outside. I just got to take them outside. We live in Oregon. What's the worst kind of spider that's here? Okay, a brown recluse. You guys saw it, did that look like a brown recluse to you? No, it wasn't a brown recluse. They're reclusive. They don't show up on camera. Alright, so, what was I saying? Besides brown recluses. Oh, yeah. So these are, you can think of them not just as necessarily hydrogen acceptors, but hydrogen transporters, because they're going to pick up hydrogens, and then they're going to dump them somewhere. That's what they do. They just carry cargo from location A to location B. So you load the truck, you go somewhere, and you empty the truck. That's what happens. And so you can reverse these reactions. You can write reduction reactions with these coenzymes, and they dump hydrogens onto a molecule or into, I don't know, what else could we say? Oh, the electron transport chain, if you know what that is, because that's where most of them end up going. So, the last thing we'll say about these guys is that they are derived from vitamins. I'm not going to go into the chemistry of this, but you have to have vitamins in your diet. They're vitalamines. That's what it stands for. So, you know, it's like essential amino acids. It's things that we have to have in our diet because we can't produce them ourselves. And let's see. So, make sure I get this right here. Yeah, so NAD plus. I don't want to write the wrong vitamin. Well, that's derived from niacin. And FAD is derived from the B2 vitamin, which is also known as riboflavin. So, a little small change. You can look up the structures if you want. I'm not going to hold you to it. But, you know, the relationship between vitamins and these coenzymes, they are going to just be slightly modified versions of the vitamins to get us the coenzymes. And then why are they called coenzymes? Well, keep in mind that when we have a reaction like this, oh, whoops, that doesn't go there. Well, this isn't the enzyme driving the reaction. This isn't catalyzing the reaction. This is like a reactant in a product. So what do we got going on? Well, we got some oxidoreductase in here. And so another way of writing this, using the format from the last section, would be, okay, I've got a molecule. I'm going to do a big reaction arrow because I've got to fit some stuff around it. And I've got another molecule for a product. Alright, so what do I label here? Well, I'd have a box down here. I'd write oxidoreductase. How do I know it's oxidoreductase? Well, one, it is definitely the most fun name to say for all of those enzyme types. But we got a redox reaction. Okay? And then we got our little swoopy arrow here. And so we got NAD plus as another reactant, right? Just like before. And then we go NADH and H plus as our other product. And so we can fill out the same information we were doing before. And so now you have a much deeper understanding. So you saw an example like this. Didn't have these guys. You saw an example of a redox reaction with oxidoreductase. And so now you can add some more information, some more understanding to it. Alright, so This is the enzyme. This is the protein right here. This is the enzyme. These are coenzymes. And then, you got your products, your reactants. These coenzymes are derived from vitamins, whereas they're also sometimes called cofactors. So they're just other large biological molecules used in the reaction. And there's something that can cycle around. So NAD plus can become NADH, can become NAD plus again, so it gets reused over and over again. Just like our enzyme doesn't get used up in the reaction, it keeps its structure. Just like all catalysts do. Alright, so next we're going to talk about acid-base reactions, and that'll be the last new type of reaction to talk about. And then we'll just kind of review and make sure that you can tell when something is combustion or acid-base or redox or whatever. Alright, so on to acid-base chemistry.